So finally, let's do some equations. We have looked at a couple, but not very seriously. This is about tropical cyclone motion. And in the media and in general talk, you hear about cyclones being steered, and there is some steering winds that exist, but this is a bit more complicated than just imagining that the cyclone is just being carried around like a rubber ducky in a wave or something. Cyclone very much interacts with the environment, and to understand that we have to first do some simplified analysis without any background environmental winds, derive some vorticity relations, and then add the environmental winds to see why the cyclones move in a certain direction, why there are asymmetries that evolve, and so on. People have used the concept of integrating winds in the upper level or in the middle level, depending on the intensity of the cyclone, to try to explain the transition of a cyclone along certain paths. And there are some fundamentals that tropical cyclones always move westward with respect to the background winds. Some of the ideas are similar to the Rossby wave idea, if you have done Rossby waves before, in terms of the planetary vorticity being a major player, because as you go from the equator to the pole, the Coriolis effect increases. There is the F term that we always talk about shown here. There is a df dy, or the beta term, which is very critical for Rossby waves as well. Obviously it plays a role here. So starting with the concept that the cyclone is basically a vortex, we make some simplifying assumptions. For example, look at a barotropic non-divergent potential vorticity equation. Barotropic basically means we have averaged it, and then the horizontal structures at each level are the same. So we have removed the let's say the slopes between the pressure surfaces and density surfaces by averaging and assuming it to be constant in height, which makes it non-divergent. So the Lagrangian equation, or the total derivative in that case, d dt of zeta plus f, which you remember is relative plus planetary vorticity, or the absolute vorticity, total vorticity, can be written as partial d dt of zeta plus f plus v dot grad of zeta plus f. So the change time derivative of zeta plus f, time rate of change of total vorticity, is related to the advection of the total vorticity by the flow vector field v bar. And typically when you do this non-divergent barotropic, the vertical velocity doesn't exist, so it's just the horizontal flow field. If you're at a location, then obviously the Coriolis doesn't change in time, only changes in the meridional direction, so the partial f over t becomes 0, in which case you can write this equation as d zeta dt equals minus v dot grad zeta plus f. This is the total vorticity. It's tempting to think that f is small in some cases, like the cyclone where the relative vorticity is large. Remember, we invoked that to make the Rossby radius of deformation small, so that as a perturbation it can survive and not get wiped out by being much smaller than the Rossby radius and so on. But the advection of planetary vorticity does matter for the actual cyclone dynamics and cyclone motion. So in that sense, the advection of planetary vorticity itself is known as the beta effect, where beta is of course 1 over a df d phi d phi. Because it's only a function of latitude, we can write it as the single variable derivative here, which is different than the Lagrangian derivatives we are talking about here. So just be careful. Sometimes we write this with capital D, but here it's small d is used. It's probably better to use small d for this and capital D for the Lagrangian or total derivative, but nonetheless. So that's written as 2 omega over a, where omega is the rotation around the axis, a is the local radius, which is related to cosine phi, or in Cartesian coordinate we typically write it as df dy, where y is the latitude in the Cartesian coordinate, right? We use x, y, and z. So we will derive the equations, but let's look at what we are doing first in terms of the beta effect. Propagation of a tropical cyclone could not occur without north-south variation in the Coriolis parameter. So this is very critical. Because of this planetary vorticity change along latitudes, the cyclone gets to move. Okay, so the rotating winds of a tropical cyclone combined with the north-south variations in the Coriolis parameter induce relative vorticity asymmetries, as we will see, because if you remember the counterclockwise flow of a cyclone, on the eastern side it is moving from low F into high F. On the western side it is air parcels are moving from higher latitude to lower latitude, so you're going from high F to low F, so you're going to create vorticity perturbations, which are going to be very important, and create asymmetries in the tropical cyclone, as we will see in a minute. These asymmetries are what will generate beta gyres to conserve vorticity. In the absence of friction, we are going to need these beta gyres. Since relative vorticity is calculated by taking spatial gradients of the vector wind dv dx dv dy terms, dv dx du dy terms in the vorticity, relative vorticity, changes in vorticity must result in changes in the winds. So if relative vorticity is changing, that means there is gradients of u and v. Hence the beta gyres must have winds associated with them. Okay, so beta effect is generating winds, which is perturbing the field in which the vorticity itself is existing. The winds of the beta gyres produce a net flow across the tropical cyclone center. So basically that's the net effect we end up getting from just having pure rotational vortex. We are now going to have, because of beta gyres, a flow across the cyclone center. Generally the beta drift is towards the northwest at a few knots. The speed and the actual direction is related to vortex size and strength. Okay, makes sense, right? Vortex, if it is stronger, it's going to have quicker motion equatorward or poleward, or equatorward, and the strength is related to that, of course. In computer modeling studies, the beta gyres initially form at the radius of maximum winds, Rmax, of the tropical cyclone and are oriented due east and west of the cyclone center. As you can imagine, we are moving towards different F on either side. On the north-south, it doesn't matter so much because you are moving along constant F. The cyclonic beta gyre is to the east of the storm center, and the anticyclonic beta gyres is to the west. And this doesn't change with the hemispheres because the cyclonic anticyclonic circulations themselves change in the hemispheres. In the northern hemisphere, cyclonic circulation is counterclockwise. In the southern hemisphere, it is clockwise, right? As the computer simulation evolves, the beta gyres move further out from the storm center and are rotated cyclonically, so that depends on the hemisphere then, because of storm's rotational winds, which are cyclonic, from their initial east-west orientation. This final location and orientation of the beta gyres results in relative vorticity asymmetries with associated winds that cause the tropical cyclone to propagate poleward and westward in both hemispheres. Poleward and westward in both hemispheres. So this is now quite far from the idea of steering winds. There is active participation of the cyclone and its rotation itself in the mechanism of cyclone propagation. Okay, in the northern hemisphere, the tropical cyclone propagates further north and west than would be expected due to steering alone, while southern hemisphere cyclones propagate further south and west. In the real atmosphere, we cannot see the beta gyres evolve in this way because it's in a fully complex 3D circulation field as opposed to the barotropic kind of simple analysis we are doing here. In reality, development of beta gyres occurs along with the evolution of the tropical cyclone and its environment. It is important to remember that the tropical cyclone will always propagate to the west compared to the steering flow, no matter which hemisphere it is in. So there is a relative motion, which is always westward. Development, or there's an absolute motion that's westward. Relative motion may get changed by the background environmental winds. Development of the beta gyres can be demonstrated using the barotropic non-divergent vorticity equation, which we started with. We will now go through that. So let's look quickly here at the conceptual model of the beta gyres for the northern hemisphere cyclone with no environmental flow. So this is the southern hemisphere, equator is sitting here. So we are looking at the cyclone propagation southwestward and northwestward, and here is a counterclockwise circulation in the northern hemisphere of a cyclone, clockwise circulation in the southern hemisphere. So here we are moving from lower F to higher F latitude. So that means the relative vorticity of the air parcels have to change to conserve total vorticity with no friction in this barotropic sense. So you need this gyre to form to try to balance the total vorticity zeta plus F, whereas on this side you are going from higher F to lower F as an air parcel, so you will need a counterclockwise circulation, so cyclonic circulation and the anticyclonic circulation on either sides. These are the beta gyres. Very simple way to think about it. And there is our main cyclone sitting here. Okay, and the same thing happens in the southern hemisphere. You can see we have anticyclone and cyclone, so clockwise and counterclockwise, opposite directions. Just be sure of that. So this figure is worth 1,000 words, as they always say, because it explains why we end up with beta gyres and why the intrinsic nature of the vorticity associated with the cyclone itself begins to produce steering towards the west and north and south and west, depending on the hemisphere. Okay, we will come back and look at the equations associated with these so we can understand better the entire mechanism of cyclone motion with the asymmetries evolving out of these beta gyres and beta effects.